So see if I can view myself completely on this one. I cannot, so it's okay. So I guess a quick review of like probability. We know that like we have some random variable. Like basically we can define a random variable, maybe x here. It just can take like different outcomes here. So maybe I can take outcomes like x1, x2, and so on and so forth. And then we can talk about the probability of like this for each of these outcomes. So we have like p x x1. That would be like the probability of like x equal to x1. Usually we will shorthand that into just p x1, something like that. So and the function of like all these probabilities is known as a distribution and depends on like or also known as like PDF and PMF, like probability density function and probability mass function, depending on whether the random variable is discrete or continuous. So now okay, we talk about like last time like okay we talk about independence when we have two random variables now, x and y. We say it's independent. It's essentially we have like px py is equal to pxy, or like usually it's written in the other way, pxy is equal to px times py. So this is the condition. So if and only if this for every x and y, then we say that like um, x and y are independent. So it's usually denoted by this one is like sometimes two stroke here. So anyway, depends on textbook. Right. So maybe I will just write one stroke here. So it's a perpendicular x perpendicular to y. Um, so we argue that like okay, this is a very reasonable condition because by base rules, I can write like pxy here as a px py given x as well. So that means that like if I cancel this x px out, then I have like py given x is equal to px py. Sorry, py given x is equal to py. So meaning that like it doesn't matter whether you know x or not. It doesn't change the probability of y. I mean like no matter like what x you're looking at, like the probability of y equal to this small y will be the same, regardless the value of the outcome of this x here. So then of course it's very reasonable then like this x and y will be independent. So this is independent. So we say like conditionally independent or conditional independence, conditional independence. So that involves three random variables, x, y, and let's say z. So we say like x perpendicular to y given z, or like x and y are conditionally independent given z, another random variable. So if and only if, typically it's shown this way, like pxy given z is equal to px given z and py given z, something like that for all x, y, and z. So, and this again, like, it's very reasonable. If we look at this other way, like using base rule, I can expand this into like px given z, py given x and z. So by the way, like you okay, I try to see if I can remove my voices. The echo is pretty annoying. Let's see. Maybe hmm, I'm sure I can do this, but let's see. I want to mute myself. Okay, anyway, I will figure that out later on. So so this again, like the base rule, like this is like another form of base rule. I know that like you definitely like see this base rule in like your first probability class as something like px given y is equal to px y over py, something like that. So, but I argue that like an easier way to remember Bayes rule and like to interpret Bayes rule is I just think of this as some kind of chain rule, a chain. So in the sense, if you have like px, y, z, it would be like px, and then you look at like another random variable y. The probability of y given big X is already equal to small x, and then pz given that like I take like big X as like small x and big Y as small y. So note that again, like this, I'm writing this like with all the shorthand notation. Like this one here is meaning like p x y z x y z something like that. But that would be like very the notation would be very clutter. Yeah, I'm meaning this basically. But usually like we would just write like this like without any confusion. So and also like if you look at like similarly, if I have like conditional probability like p, let's say x y given z, I can have like this similar chain rule here. I can have like p x given z here, then p y given x z. Yeah. So okay, now back to the conditional independence. So if I have this is basically the Bayes rule that's always true. This is the condition for conditional independence. So I have therefore like I can have px given z can be cancelled out. Then I have like py given xz is equal to py given z. So meaning that like if I know z already, it doesn't help me to kind of like you can say to predict the value of y. I mean like given z, x doesn't help you to predict y. So maybe I'll give a couple examples that become obvious. So let me give like one example. Like I'm trying to give an example like last time. So I stopped there essentially. So let me give an example like this. I will start with just a coin here, a coin. So it can flip it like have head or tail. Now I also have a dice. I'm not saying I start with like just the coin. Like I start with like I'm going to have a hat. Like I just put a coin and turn the face of the hat to the sky. Like yeah, I mean on top. The have the hat on top. Now I throw a dice. Let's say I have a dice. I throw it, and when I get a 6, so I'm going to flip this coin. So I'm going to flip this coin whenever I got a 6. So and that first time I do it, like I got a random variable x, let's say, and then I do it the other times. Again, I flip. I throw a dice. I see the outcome. If the outcome I got a 6, I will flip it again. So for example, like if I in this case I got a 6 here, so I flip it or got a tail here, and then the second variable, let's say I call it y. I got a 6 again. I flip it. I got a head. Now I do it again one more time. Let's say, oops, I should say I got a 6 here, 6 here. So maybe I got a 4 here. So I got a 4, I'm not going to flip it. And let's say these variables, after I'm doing this third, following this dice, I call this outcome like z. So I have like, let me repeat again. So I start with a hat, and if I throw a dice, if I got a 6, so let me write out also. The rule here is like flip coin if dice is 6, let's say. So I do it 3 times, let's say. I throw it the first time, okay, I throw the dice first time, I got 6. So then I flip the coin, I got a tail here. I throw the dice again, I I got a 6 again. Now, so I should flip this coin. So I got a hat again. Sorry, I got back the original hat. And then float again, I got a 4. So therefore, I'm not going to flip the coin. So is that clear, the setup? Maybe I just make a very simple question. Just make sure, like, what you see, like, what's the probability of x is equal to tail? So this is like the first question. I hope you guys are still here. I know this is a long introduction. So let's see. I need to find. No. I'm redo it again. So this is just one example. This is one example here. I may have another example. Maybe I thought it the first time I got a 4, and then I got a 6, and then I got a 1. Then my x will be equal to hat, because I didn't got a 6. Right? In this case, a hat. Then this is I got a 6 the second time, so I flip it. I got a tail here. So then Z is a tail again because I thought the third dice is just getting a 1. So this is in this case I will have x is equal to head, y is equal to tail, z is equal to tail, something like that. So this is really a warm-up question. Like this should be very simple question, but I just want to make sure you um, I'm clear with the setup. So we only have one. Okay, one dice at a time. We throw one dice at a time. We throw the first dice, right? And whenever I got a 6, I flip the coin. Then I throw a coin again. If I got 6, I flip the coin again. If not, I'm not going to flip the coin. Then I throw the dice like the third time. Again, if I got a 6, I flip the coin. So I just repeat this 3 times essentially. And the first times I got the outcome, I call the variable x, and the second time I got the the outcome of the con, I call it y. The third time I call the outcome like z, something like that. The dice is assumed to be heads, like right at the beginning. Okay, this is fixed. So I assume this con to be just facing have the head uh, over. Okay, how do you call this? Like it's head at the beginning. Yeah. So I'm starting the con as head. It has nothing to do with the die. So okay, the die um this one is fixed, like this one is fixed. So if you put a random variable here, if I call this W here, basically the probability of W equal to head is equal to 1, something like that. So I'm okay. The rule here is like only with like the dice outcome is 6, I'm going to flip the coin. Uh, wait a sec. Why 112? Like everyone like okay, this dice is the dice. Okay, maybe like I don't have the same kind of die like with you guys. So the die I have as a kid is I have like 6. Yeah, I only have 6 values. Um. Oh, I see. You have this 112 thing. Okay. Yeah. Okay. The result should be 1 1 1 1 6. Yeah, I'm thinking why you get one half there. So um. Yes. Okay. Okay. I hope this is clear. At least the setup is clear. Yeah. If your dice is like the regular dice, like a cube, have 6 faces, so that then wait a sec. Like actually the value is not wait what? Yeah, I'm true. Yeah, it's true. Since it's a dice is 4, wouldn't the con not be? Oh, no, this is just 2 examples here. I put in 2 examples here. So this is like one realization. You can think of this is not a realization. So So like you repeat this experiment multiple times, right? Each time you have something different. So this is just one of these examples here. So but the question is like, okay, what's how likely you will get the con to be the con to be tail. Then in this case, like yeah, 1/6. Okay, say a yeah, it's it's obvious. It should be quite simple. So now a little bit more challenging question. So what's the probability that like why oh why to be 1/6? Okay, I have this basically the value depends on the die, right? Oh no, actually the problem first of all like there's two things I may lead to confusion here. First, like actually if this um the setup here, maybe I start with like this the original setup here. My original setup here is like W is fixed, right? So it's a hat from the beginning. The probability to get W to be a hat is one. So because it's hat, I start with that con is hat at the beginning. So to get it to tail, you can only get a six, right? You cannot do anything else, right? Uh, let's think of like another variables. I call it U here is the dice outcome here. So probability X is equal to tail will be equal to does the con toggle not random? It's not random. Okay, as I said, like right at the beginning, like PW equal to hat is one here. I assume that I'm not going to throw the con here at the beginning. But actually, be careful. Like even the con at the beginning is random, that answer is not correct. 112. If you think of that way, actually, in that case, the answer should be one half, right? Because uh, if you start with like this is you think of that the question, then it would be more or less symmetric. Um, because I you have a chance to see like if we start with a hat. Yes, it's not random conflict. Okay, yeah, it's not a random conflict. The original setup, yeah, it's not a random conflict in the original setup. But I also want to mention that like if it's a random conflict, then 112 is still not a correct answer. Um, yes, okay, okay, make sure that like okay, maybe let me before I talk about the second question. So let me I add this new question here. It's like this. So okay, I hope everyone is like clear with the setup. But like now I am going to change this setup a little bit as what you all originally thought. So let's assume that like W is also random as well. So I start with the count, the probability. Let's say if I change this here, this is the second question now. So in this case, like the first question is like probability of W equal to hat is one. So it's like always hat, like to start with. So if like this is like I first toggle this con first. So I have probability of hat is equal to one half. So same question, like what's the probability X equal to tail? So yeah, okay, if you think it's 112, then how about what's the probability X equal to hat? Yes, then something doesn't add up, right? So you have to have like, okay, X like it's just a conflict, right? It can be either not quite right though. First of all, like, X is like the outcome of a conflict. So it can either be head or tail. So if you think like both of them is 112, it doesn't add that way. So because like it can only be head or tail. So therefore like I have like probability of X equal to tail plus probability X equal to head should add up to one way. Yes, it's one half. Yeah. So I hope you kind of see that like it's actually symmetric. No, actually, it's not. You okay? This is a let's see, like we can do it like engineering way. So engineer is like in the sense we don't think a lot. It's just like do according to the rules and calculations. I mean, if you fix the rule, we start with the rules and see what happens. So let's see, like we know that like let's see, like if I think of it as an engineer, so there's a conflict. No. Wait. The setup is like this. So for question two, the setup will be like I'm going to flip the coin first. So now W is the outcome of the coin. It can be head and tail, each with the same probability. Then I'm going to throw a dice. The dice with if I got a six, I'm going to flip the coin. If not, I will keep the coin like that. So if I do that, then yeah, then I will get the outcome X, let's say. Then the question is like, what's the probability of that X equal to a tail and equal to head and so on. Now let's say if I just focus on like what's the probability of X equal to tail. Now probability of X equal to tail is X equal to tail, W equal to head plus probability X equal to tail, W equal to tail, right? So this is I just do marginalization. So marginalize. So remember, like this is one thing we mentioned last time. If you have a random variable, like x and y joint probability, if we sum over one of the random variables, let's say y here, if sum over all the y's here, so we'll just get back px. Oh, sorry. Something like that. So because w can have only outcome head and tail, right? So this is I'm just doing the marginalization, right? So I have like this is equal to this guy here, right? So you everyone's following me for this step. So what is this guy then? Like what's px tail, pw head? So I can use base rule. I use my version of base rule. It's like a chain rule. So it'd be like probability w equal to head, probability x equal to tail given w equal to head. So now, okay, I have another question here. So what is this? This is a question 3 here. Okay, question 3 is what's probability of x equal to t given w equal to h? This one, yeah, this value here. What's this conditional probability? What is this one? So you all agree with that? Yeah, I guess it's reasonable, right? That's the setup of the problem, right? So if I'm going to, we got the W is hat, right? So we only going to flip it, become a tail. If I'm only if we throw a dice, we got a 6, right? And the probability of got a 6 is just 1/6, so it's reasonable. Yes. And then now let's look at the other expression here. I have probability again like W equal to tail probability of x equal to tail given W equal to tail. So what is this? So this is question 4, let's say. So anyone else? Oh, sorry about that. Like, uh, yeah, it's uh, let's see if I can write it a bit better. Mm, yeah. Oh, oh, do you mean this precise? Which precise here? You mean this one sign here? Yeah, 5, 6 is correct. So wait, you should agree with that way. Again, it's just according to setup way. So originally it's a tail. It's still a tail. It happened if like I don't get a 6, right? So therefore the probability will be 5, 6. So then you see I have 5, 6 here, 1, 6 here, and this is just 1/2, right? So if I add that, I will just get 1/2. So therefore you see the answer for the second question should be 1/2. So okay, now let me make a new page here. Repeat this a little bit. I have W here, right? So the con, but I will go back to setup 1. So this start with this W is just a hat. So probability of W equal to hat is 1. And then I will got a X here, basically a forward dice here. That get various X here. Then I got a Y here, again I forward dice here. Right? So if I get a 6, I flip it, then I flip a 6, I flip it again. This is this is called Z here. Right? So now another question here. What's the probability of Y equal to hat? So I want to emphasize this one here. Let me, maybe, how do I do that? I don't know. So I want to change the color of this thing, but it seems difficult. Um, maybe I just, oops. So I want to emphasize this. So this is I guess question 5 or something. Yeah, sure. Um, the question, do you get to set up the first setup? Basically, I have the original setup is I have a con. The con is at the beginning is facing is hat basically. Hat is facing above. And then I throw a dice. Uh, when I throw a dice, I got a 6. I'm going to flip the coin. Then the outcome I call it X. Now I'm going to do it once again. I throw the coin. And if I got a 6, I'm going to flip the dice again. And then this time I call this Y. Then I'm going to do it again. If I got a 6, I will flip the coin. Otherwise, I will keep it the same as before. Then I call this Z here. Now, the question is simply, what's the probability of Y to be hat? So you guys are all finished? I don't know. So I think most likely Sarah's question, Sarah's answer is correct. So let's look at this again together. So we have Y is equal to hat. How can I get a hat? I start with like uh, W is a hat, right? So if I got X is also a hat, so basically if I can have PY, how can I draw this more graphically? So I start with like W, let's maybe just draw here, like W, X, Y. I start with this is a hat, right? So I ended up like Y is a hat. I can either um hat, like if I got flip once to tail and then I flip it back to a hat, then I'll get a hat, right? The other possibility is like if I don't flip it, I didn't need to flip that, so it's hat. Then next time also I didn't flip it, I got a hat again. So then I also will get a hat. So that's two different ways I can get a hat like for Y. So therefore like or I can repeat what we did like previously. I can do marginalization. I can write this as a Y equal to hat, and then X equal to tail plus probability Y equal to a hat, X equal to hat, right? And and conflict becomes random after first fit. Uh, oh, yeah, okay. I guess still like maybe I'm not very good articulating the setup. So I have this the con here is just like uh it's you can think of just 0 and 1. Like it's I use a con. I think it's a little bit more descriptive, but you can think of something else. But I have something like whenever I throw a dice, if I got a 6, I flip the number basically. So, and then I do it several times. That's just what I did here. So now if I go back to this expression here, then this is equal to what? This is equal to probability x equal to tail, probability y equal to hat given x equal to tail, plus probability x equal to hat, probability y equal to hat given x equal to hat, right? So for this one here, because W is hat at the beginning, right? To got it flip, the probability is 5, 6, right? Now, oh, wait. Got it flip is 1, 6, right? Sorry about that. Mm. Got this flip is 1, 6. And then for this one, like if X is already tail, as X is tail, to get Y to be hat, like I need to flip it again. So I got 1, 6 here. And for this one, this is a 5, 6, 5, 6. I guess I several you got it correct. Right. So therefore, like I will get this is I think that what you have here, 13 over, oh yeah, 18, something like that. So now I also have a thing Z here, right? I repeat this, I have a uh do it one more time to get another outcome Z here. Now let's see. What is let's look at another question here. What, still I have the same setup here, exactly the same setup. But what is z equal to hat given y equal to hat, let's say? Should be simple enough. Yes, it's not supposed to be a tricky question. Yeah, okay. So now let's look at another one. Very similar. Probably c equal to hat given y equal to hat and x equal to tail, let's say. So what is the probability for that? Yeah, it's true. Yeah, I haven't had my coffee as well, so please forgive me whenever I make mistake. You know. Yes, that's the point actually. Uh, you as you see, like if I already know the value is hat here, like it doesn't matter what x is. It can be hat or tail. Like actually in both cases here, this one hat given y equal to hat is equal to hat here will still equal to 5, 6, right? It's still equal to this probability and y equal to hat. So actually, you see in general, I will have something like that. P z given y is equal to p z given y x here. So this is a precisely the condition we mentioned earlier. Um, there is a z and x are conditionally independent given y. And okay, maybe another question is like no probability here, but just a question like is x and z independent? You can try to verify that, but wait, but I guess one thing to verify whether something is independent, you can think of this that way. Um, if of course, you can try to show whether like PXC is equal to PXPC, something like you can compute this and compute this and see whether it's true. Or as I mentioned, like if this is independent, then you should have like PC given X is equal to PC, right? So because like this one by base rule is just PX PC given X, right? If I got PX cancel, I will have like PC given X is equal to PC here. Mm. Now, is this true? Now we can try something, right? So let's say um, if X is hat, just think of some special case here. If X is hat, and mm, let's see, X is hat. Is C more likely to be hat or tail? Let's try it. Let's think of this. Like, what was this one? Or maybe okay, maybe this is not a very good example to try to explain this. So let's look at this instead. Like, what if X is tail? And look at this one here. So do you think like it's more likely to be uh, yes, actually it is. Okay. Yeah, okay. That's actually that's the point I want to point out. So if X is tail, C become more likely to be tail than original, right? Because I okay, originally like think of X as X is actually quite likely to be hat, right? Remember, like you only have 1/6 probability to got flip um from head to tail. So for this setup, because I originally W is hat, so actually, yeah, they are not independent. So because I when X is a tail, then I it's actually more likely C now is tail than it originally supposed to be. So of course you can try to I don't write it out, but yeah, you should get a number like that. So but therefore, like one thing you should be very careful. Like uh, this is one thing. I think like this is a take-home message, right? To very important for this class because like this is a mistake like almost everyone made at some point, like learning probability. So is that like easy to confuse like independence with conditionally independence? Um, it's there's a tendency that like thinking, okay, if I have something conditionally independent, then maybe like it's independent. So this is wrong. How about the other way around? Okay, this is a question. Is that true or false? Do you think? If something is independent, is that conditionally independent? So my question here is, let me just write it out. Uh, X independent, then X C conditionally independent given Y. So so we know that like if like something is conditionally independent, it doesn't necessarily mean that like it's independent. Like if I have X and Z are conditionally independent given Y, it doesn't necessarily mean that like means that like X and Z are conditionally independent. So how about like just like independent? Like if X and Z are independent, does it means that like I can have like X and Z are conditionally independent given Y? Yes, actually, that's the thing. Like these two, you can think of the these two conditions. Like they are independent. Actually, you can think of that way. They they don't imply into one another. So you have to be really very careful. So I can give an example, like a counter example for this. So um, so already like we have a counter example for this one, right? So if I have something, yeah, 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 it's okay. Like yeah, I realized that like in graduate school as well, like I made these mistakes like in undergrad. I didn't realize that. So I saw all this independence, conditional independence. I learned it like undergrad, but I yeah, I also made this mistake until uh yeah for a long time, honestly. So yeah, just one very simple counter example. Let's think of like let's see. I can just count flip. So let's say I have x, y here, x and y. But let's denote the outcome as 0 and 1. Let's say 0 and 1 here. So if I flip the coin, I can get like either 0 or got 1 or got y is also either got 0 or got 1 here. Now I define Z. So I assume that these two are independent. So just from the setup, I assume that X and Y are independent. So you independently flip two coins and get the outcomes. Whenever you get head, you say X is equal to 1. And if it's you got tail, then you got like you say it's 0. Now I let me define a new variable Z here as just like the X or Y here, something like do an XOR operation. So I have the XOR table is something like that, right? Let's see. Let me how like that 0 0 1 something like if I XOR something and 0 1 1 just something like that. If I have like X XOR 1 is like 0 XOR 0 is 0 something like that. Like I'm sure you know what I'm talking about. So know that like okay because like X and Y are random, of course Z is random as well. Now, I definitely have X and Y are independent with one another from the setup, but I don't have like X, Y conditionally independent given Z. This is not true. It's, you can easily see that why this is not true because the XOR operation, if I have Z is equal to X XOR Y, I can write X XOR Z is equal to X XOR X XOR Y, something like that, right? So XOR operation is associative. So I can do this first. X XOR X is just equal to, wait, it's just equal to 0, right? So 0 XOR Y is just equal to Y here. So I got back like y is equal to x or x or z, right? So what does that mean? It means that like given for conditionally independent, how do I see this? It's saying that like knowing z, then wait, wait. What I try to show? I suddenly got forgot. Let's see. Y x conditionally independent given x given z here. Oh yeah. Okay. Now this is not true because given z, what does that mean? If given z, then y definitely is very the exact opposite of independence. I say very much depend on y because if you look at that like depend on x or like I put it, y will be very much depend on x given z because like y is essentially just equal to x or z, right? So if given z here, if you know y, then you know x precisely. There's no way there's something we call independent, right? So if you mean independent, you know something, it has nothing to do with another thing, right? That is independent. But here it's like if you're given z here, you know one variable, you know exactly the other variables, then there's no way they're independent to one another, right? X, Y cannot be independent, conditionally independent given z, right? But X and Y by themselves are independent. So yeah, this is like one kind of classic example, like for like something is like independent but not conditionally independent. So okay, maybe one final note here for this thing uh, is like to mention this something known as the Markov chain. Markov chain. So here is an example of the Markov chain here. So I can repeat this experiment many times, right? I have the experiment here. I can continue to do that. Maybe I have like wxy, maybe I have another variable u, v, and so on. And you can see that like I basically uh, again, maybe just make it concrete here. U is I got it like by throwing another dice, and I only flip the outcome of C when I got a 6, and V is I do the same thing. Like I only flip the outcome of U if like the dice is 6, something like that. So you see, like for this entire kind of like a sequence of experiment, each of these variables are conditionally independent of like variables like kind of like before the last variables, as long as we are given the last variable. So what I mean is I will have V conditionally independent given Z. Oh, sorry, V is conditionally independent. Wait. Let me write again. Yeah, it's true. Yeah. V is conditionally independent of C given U, something like that, right? And actually, V is also conditionally independent. Okay, this is V here of y, any earlier variables, actually x, y, z given u, something like that. And I have like u conditionally independent of y given z. Yeah. Now, this like we call this Markov chain. You see like each of their variables here is conditionally independent of all the variables before this, given the previous variable, all the variables before the last variable, given the last variables. And we can denote this with a notation like that: w, x, y, z, u, v, so on. So, and depending on textbook, Sometimes you see this is a an arrow like on one side the arrow, like maybe just pointing to the right, or like maybe you can see just a slash here. Maybe like some book will write like this, and sometimes like some book like write double arrows. Actually, I kind of like the double arrow notation because I it's uh, more descriptive because I know that like if you have a Markov chain like this also imply a Markov chain of like the exact opposite order. So meaning that I also have like V, U, Z, Y, X, W. Meaning that like for variable W, given X, like the rest of the variables are not in the not important. So this is Markov chain. You see this again, and but it's very simple idea. So if you see that, you see it's just meaning that the variables you have a list of random variables, and the random variables they any one random variables. If you just pick uh condition on like a previous variables, then this the variables before that is all equal or independent to this variable x here. Uh, maybe okay. This is a maybe you need a little bit thought, but a question that hopefully is not unreasonable to ask. Like, so how about like given a Markov chain like this, do I have like W conditionally independent of Z given Y? Actually, you can use this example to just like as a special case to think of this. Like, okay, if I have a sequence of experiment like this, um, actually maybe like I tried this, like maybe V condition is that conditionally independent of Y given Z. So V is here, Y is here, given Z here. So are these two are conditionally independent? Yeah, this may be a more difficult question because this is the first time to see, but it's okay. Like I want you to think a bit because if I just talk about that, like probably you won't remember that. Like, oh, actually, it turns out this is true. Just think of this example like as an illustration. Like I guess in general, it may be a little bit not obvious how to. You can show that, of course, like if you write out um whatever Markov chain means. So whenever I write the Markov chain, it's actually meaning that like, for example, like in this case, okay, I probably need to erase something or like, yeah, maybe I erase here. So the Markov chain actually means that like if I write something like this, like from a Markov chain, like this one here, I will have like PV given U, given like all the variable before that, like let's say W, X, Y, Z will be just the same as like PVU, something like that. And also like I have like PU given Z and also like XYW will be the same as like just PU given Z. And you can just use this to show that like actually P V given Z and X Y W will be equal to P V given Z. So sorry, like this is V here. So using this, like you should be able to show this. But just think of like more intuitively, like this example here, using this example, like always come back to this simple example. So if I know here, like I want to predict what's the value of V here, and now you know this outcome of C now is a head, then everything before that is an important note, right? The information like before that, like whether X is actually head or tail, like or it's a tail or head, or like it doesn't matter anymore. If I just want to know whether V is head or not, if I know Z is a head, then yeah, all this information now is redundant. It's not necessary. So therefore, like you see, like actually Markov chain is pretty strong assumption here. So essentially, it's like always if you, even though the original assumption is like if you know the previous one, all the rest like before that is unimportant. But from this one, you can easily derive that like if I don't know this one, but I know the one before that, also like the variables before this one before the last one, uh yeah, the all the variable before the one before the last one and the last one will be unimportant. So okay, like this is conditional independence and Markov chain. We'll come back to that. Hopefully, you will get more and more familiar with that and Markov chain. And we uh, basically, yeah, I think you have chance to get more familiar with that. But at this moment, I guess the most important thing is you need to realize that like independence does not imply conditionally independence, and also the vice versa is true as well. It does. I mean, like vice versa is not true as well. It cannot. The one does not imply the other, and also like um, the what the interpretation of conditionally independence is just if you're trying to predict like three variable here x, y, and z again. So if I x and z are conditionally independent given y, it's just like if you're trying to predict z here, knowing y, then x is not important anymore. Think of this, like you use this have this concept in mind, then it's very helpful. Like sometimes you don't even need to get into the math. You can use this intuition to realize whether it's independent or conditionally independent and so on and so forth. Okay. So and I guess like let's see. Next thing I want to do is a slight digression. I don't know whether I can finish that, most likely not before the break. Um, so oh, by the way, should I do some logistic thing instead? Like because I have 5 minutes before the break, maybe. So uh by the way, like you should be able to find my website, like course website from the canvas link, and then like uh you should be able to find the video recording of the lecture under Canada. So because some of you guys seems not able to find that, um, and what else? And yeah, I guess I think like the enrollment it should be more or less fixed. Let's see. I have here. Uh, I believe the number of enrollment about 6 or 7, something like that. So I guess it's 7. So probably we'll use 2 days for presentations. If you took my class before, I would like someone students to present. Usually, like presenting anything is like the best way to learn something. So maybe just for the moment, trying to fix a date, kind of approximate date, like for presentations. Um, so I am looking at mid-October, like sometime mid-October, maybe uh maybe 13 and 20th, like I don't know, like around that time, I guess I. So the thing is I would ask you guys to send an abstract of your presentation maybe 1 2 week ahead. So maybe so therefore the abstract may be due like near at the end of this month. And then also like the presentation basically you will be peer review, like peer graded. So of course I will fill in the grade, but like from the past experience and so on, like you guys are judgment are pretty good. So I usually will based on your evaluation, like fill in the final grade for presentation. And you can present like more or less um um what I mean is like okay, one thing like uh as I mentioned, like you can definitely present packages. uh Maybe let me just uh uh so So as I mentioned, you can present packages. For example, like there's some you can find other packages online. That's just some recommendation that you can look into. You can check out those packages and maybe like try to go through it a little bit and see like if you find that like kind of like you would like to present that. Another thing like you may try to uh some topic is interesting to present, so you can just go through um, a very good textbook by like Mackay, uh, Professor Mackay. The book is actually online. Uh, Unfortunately, he already passed away, and the book is like yeah, the entire book is online, and I'm basically like this is not the textbook I'm using, even though I recommend this book. Um, I mean, I don't really have a really a textbook, but like the for the materials, I especially for the power of information theory, it's more or less mostly based on like Coughlin and Thomas. That's the classic textbook on information theory. But for the rest of the materials, I just like grab here and there and so on. And for Mackay, he was trained as a physicist, and and he basically have a different perspective on information theory, and he has this very nice textbook and written in a pretty entertaining way. So I think like if you don't like to present packages, you can look into one couple chapters and probably you can just like present the chapter instead. So and with very high chance like there will be no overlap with the materials like we're going to discuss like, in this class. If you just want to make sure that like it's not going to overlap with what we're discussing in the class, you can either look at the previous offering of this course, or like you can just go to the course website. This is like a copy from the previous offering, more or less. But this is more like the material like we cover and like likely to cover also. Uh, so I'm thinking like in terms of presentation day, probably around this year, like maybe 13, 20 years, somewhere like around that. Um, and and then we probably use 2 days to present that, and then we may not use the entire class to do that. So the presentation may last a half an hour, something like, and maybe one day before, one day 3, and then I can still talk about some other materials after the presentation is done. And and also like in terms of midterm, uh, tentatively is here, but you, okay, like you guys can think about that, like whether you want to move uh to like, I mean like maybe like on 10th, or like move a little bit earlier. It's okay with me as well. So okay, like spend some time already. Like let's take a break, uh, and come back like 4:30. So then I'm going to talk about something else. Probably actually I would like to talk about life based uh algorithm, a very simple machine learning algorithm. But like since we talk about independence and conditional independence, I think it's a good digression to talk about life base. So okay, so I'll see you guys. Oh, I see some. Okay, I didn't see your. Sorry, like I will talk about this Markov chain again. I see you. I didn't really saw your comment. Yeah. Okay. So okay, let's continue. And so I guess I okay, to make my tab co-host. Yeah. So oh, okay. I guess I maybe it's good for me to after all show that like what I claimed about conditional independence like earlier, because I see some of your question there. Like I have still have some doubt here. Let me just say use this x y z w. What I just mentioned is like okay, if I have Markov chain like this, not just like W will be like independent, conditionally independent of X and Y given Z, and also like W will be conditionally independent of X given Y, something like that. Basically, this Markov chain actually also like it imply this one, right? So imply this chain here. So I should have like P W given Z and XY should be just equal to P W given Z, and this also like P and Z given Y and X is just equal to p z given y. Now, see, I need to, sorry, I need to make sure I pull out your chat so I don't miss it. Yeah. And so now let's see like this, like p w given y. So what I'm claiming is like w and x will be conditionally independent given y. So I should have w probability w given y and x should be just a probability w given y. So I don't know whether this is true, but I'm claiming that using this is true as well. So I can show this basically. So let's see. I have, let's say this one here, the probability of w given y and x is equal to p w c x y. This kind of trick is used all the time. So basically I add a variable here, but then I just marginalize it. So I have c here is like a dummy variable. I add this, but later I marginalize that, right? So these two will be the same. And let's see, this is c here. Just try to write a little bit better. And then I can decompose this, right? So using chain rule or base rule, I like to call it just chain rule. So this one is like p c given xy multiply pw given c xy. So this is always true basically. So this is just base rule here. Essentially it's just base rule. Or like a generalized base rule, I call it a train rule. And but then you see like this, I already have this here, right? It's just pz given y here. This is pz given y. And for this one, this is a pw given z. But note that I can also put a y here. It doesn't matter because it's actually like given z, it doesn't depend on x and y. I can remove both x and y, or maybe I will put like just one of that. It doesn't change anything. But if I write like this, then this one using base rule again, this is like p w. Let's see, c given y, right? Now I sum of c again, so c got removed, so it's like p w given y. So that's basically saying that like this variable given y here will be conditionally independent given x here. So okay, so hopefully this kind of like make you some more imprint about conditional independence in your whatever. Yeah. So okay, as I mentioned, the next thing I like to talk about is life-based. Is a slight digression. Life-based algorithm. So it's a machine learning algorithm. Like for those like who doesn't know anything about machine learning, it's just we try to build a model to train the model to do something using just the data alone. In this case, this is a classification problem. So I have like several different classes that I have an incoming object. I want to classify the object to whatever classes based on some features. So let's say I have some object like O, and I have like F1O is like the first feature of the object, like F2O is the second feature of the object, and so on. Right. And then the class of that object may be CO or something like that. So here, like O, I assume to be random. Like maybe I randomly sample an object from a population here. I just, I don't know, select an animal from the forest, and then I'm trying to classify it based on different features. Maybe like does it has long tail and short tail and so on. So this can be like features saying like it's a long tail. Like this is a function to say like the length of tail, then it can be long or short and so on and so on. So, and based on these features, I'm trying to classify that. So to simplify the notation a little bit, I will just uh no, okay, one thing. Because I always a random variable, F1, F2, and so on, all these are random variable. MC as well is a random variable. So I just say from now on, I will just write like this, like F2, C, and so on. So even though like it's understood that like the randomness coming from uh the object you are picking from the population, right? But this like the features themselves are random essentially. But yeah. Okay, so the light phase, what our objective here is like given this F here, we are trying to figure out what's C here, right? And a very reasonable way to do classification will be simply look at the conditional probability of C given F1 up to Fk, right? So I look at each of the feature and look at the conditional probability. Maybe C have like several classes, maybe just cat, dog, just three classes and pig, let's say, right? So it can be like C, D, and P, let's say. Can take value. Okay, maybe it's better to have lowercase. Or maybe just C. Yeah, maybe like cat is C1, C2, and C3 here, right, for different classes. And then like I can like compute if I know this one, and I can compare which one is have a highest probability, highest conditional probability, right? For example, if like P cat or PC1, F1, FK is largest, is bigger than like P dog given F1, F1, and P pig given F1, and so on. Then I will pick this is the class, right? So this is something very simple, very reasonable, right? So then the question becomes like how to find this conditional probability, right? So then we can just simply use Bayes rule. That's why the algorithm called like live Bayes, right? Well, why it called Bayes essentially? So I use Bayes rule. So I have like PC given F1 up to Fk. Let's say K features here is P C F1 Fk over PF1 Fk. Okay, here I cannot do much yet, but I can expand in another way. Let's see, I expand this as a PC and then PF1 up to Fk, what it given C over F1, PF1, PFK, right? So, okay, so this still like finding this strong probability can be complicated. So one big simplification is like, okay, let's assume that like F are conditionally independent given the class. So let's say I can assume that F1 given, let's say in general, Fi given Fj are conditionally independent given the class C here. So if I assume that, then this become like P, C, P, F, P, F1 given C, P, F2 given C. Oh, okay. F2 given C, and so on, right? P, Fk given C. I might have a denominator here, like whatever. But note that this denominator does not depend on C here. So what I try to find is like the optimum class, right? So therefore, like the denominator here is like irrelevant because it does not depend on C at all. So, or I can even just think of this is like, this is proportional to this thing, right? Or equal to some constant. That constant does not depend on C, multiple this guy. And actually, it turns out like it's, I know that what's the constant. The constant should be just a normalization factor, right? So because I have like P, um, because like this thing here, wait a sec, let's say let me write this again. So note that like this one here, this one equal to this guy here. This is a conditional probability of C, right? So what is sum over all class C here? What's this? Okay, this is a question here. What's the sum of conditional sum of all these conditional probabilities with respect to C? Yeah, so it's just sum up to one. So therefore, like, okay, sum up to one. So if I substitute this guy is equal to whatever, then K will be just like equal to, therefore K should be just equal to, or like maybe I put K like at the denominator here over K. So then K should be just equal to like sum over C, P, C, P, F1 given C, P, F2 given C, and so on. P, F, K given C. Yeah. Right. So this is a life-based algorithm, very simple basically. So you see, like the thing we're doing is like we are just using one assumption here, just assuming conditional independent. So assuming that like the features themselves are conditionally independent given the class itself. And by the way, like I find some numerical example online. There's a blog post by some guy like I think he gave a very interesting numerical example. I may go through that. But he actually made some, I shouldn't say mistake, but like he 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 used another assumption like that is not needed here. As you can see here, he also assumed that like Fi and Fj are independent. Actually, this is not quite true. Like if I apparently like all the features shouldn't be independent. For example, like if you think of like trying to classify an animal, uh, um, whether it has wing and well, let me think of like different features. Um, whether it has like a beak, like is that how do you call the beak? Is that peak or beak? Like it's like for the bird, and also whether it has wing. Apparently, these kind of features is closely related to one another, so therefore it cannot be independent. But in his derivation, basically, if I assume like things are independent, so therefore this can also expand to like p. Okay, make this product like into like product of pf1, pf2, and so on. So therefore, this expression like simplified to p this over pf1, pf2, and so on and so forth. So this is a kind of overkill doing this. Like you don't need this assumption because this is just a normalization factor. You don't need that. So as I mentioned earlier. So but anyway, like let me just use this example here. Though like even like his description is not completely
Dr. Cheng.
um
Dr.
I
Cheng.
shouldn't say like incorrect, but like he kind of like introduced assumption that is not needed. So he has an example like this. Let me just oh, let me see if I can copy that. Okay, let me tricky. Yeah, that's the example like he kind of like he created. So it's just like trying to kind of like classify several like different food here. Actually, the features I no, yeah, yeah, it doesn't necessary. The features are not independent. So in the original formulation, you don't need that to be independent. Um, of course, you can make that assumption, but yeah, okay, it's just you shouldn't make that assumption. I don't think like it's a good idea to make that assumption. As I mentioned, if you have a bird, like let's say if I was trying to classify an animal, have a bird, like maybe it has a beak here, it's like you call it beak here. And if you say like an animal like with a beak and also like with wing here, most likely these two features are highly correlated, right? So depends on like whether it's a mammal or like a bird or like something like that. So therefore in general like features are not quite kind of independent with one another. But conditional independence probably is not a too bad an assumption. So given a particular class, like you think of like the class, for example, is a bird or cat, like given that it's a bird and a cat, then um those features like probably are conditionally independent. Like in the sense like knowing that this is a cat, then you think of like the cat eyes is likely to be like that, right? So if a dog like the eye is likely to be like that. So and they are conditionally independent in the sense like knowing that it's a dog. So when I think of like conditionally independent, would be something like that. Let's say if I description of an eye and an ear here. So maybe an eye here and an ear here. So knowing that it's already a cat here, it doesn't matter like what the cat's eyes look like. I can describe the ear of the cat like pretty well. So does it make sense? Of course, like if your description of your class is not very fine in the sense that you can think of like different species of cats, like subspecies of cats, then they may have a very different ear. But maybe I have the class is a pretty fine, have a fine granularity. Then um, given the particular subspecies of the cat, I can describe pretty well with the ear without knowing the eye of the current object, right? So then in that sense, they are actually conditionally independent, the features. Yeah. So, but anyway, like this, of course, is still just an assumption. Even for conditional independence, it's assumption. Therefore, like you see, life base is it's very efficient, but it's not the best algorithm out there. So, but it's like the very good algorithm to try in the first step, I would say, like because like it's very easy to implement. So this is just an example here, right? I have as I mentioned, trying to classify fruit here, like I have banana and orange and others, I say, and depends on like different kind of like shape and whatever. Here, say whether it's yellow, whether it's sweet, or like whether not sweet, or whether the shape is long or not. So, for example, like for orange, like if all of them is not long, and banana like very damn long and something like that. So then essentially I have let's see, I have like three variables here, right? Or like three features here. This is like whether it's long or not, or whether it's sweet or whether it's yellow, right? This can take a value or true or false or like 0 and 1, right? So this value can take different values here. So then I can say what's the probability of getting a class of banana, let's say, based on like that. I can have like class is like banana based on like the feature L, S, and Y, where it can be uh, for shorthand, let me write it this way. Like, so if it's log long, I will write like this. Log short will be not like that. Log yellow, this is not here. This is also a logic notation. I guess you see that before in other class. This is not here. So like some class use that. Maybe I can use question mark also. Maybe I use question mark. Right? It's like a programming, something like that. So it's a question mark. So it's not something. So then the probability of, for example, I can ask like what's the probability of banana given that it's long and also like have features like sweet and also yellow, right? So based on this table, like what should be the probability here? Um, I can find uh basically I can find what's the probability of uh what I want to say is like this will be proportional to probability of let me write the whole thing here. Let me write from start. Like so this will be what? This will be like PBLSY over PLSY here. So maybe I just call this constant K here. So it's not very important. I mean, it does not depend on the class B class here. So this here is like the class I can take value. Let's say you can take value like banana or orange or other. That's pretty bad. Maybe other is like just course is other. So maybe this course is other. So I can take these three different values here. Let's say, and what I'm interested in is like based on like these features I observe whether it's a banana, whether it's orange, or like whether it's others, right? Now I know that like this should add up to one, right? POLSY and PXLSY should add up to one. So using that, I can kind of like figure out this normalization factor. So I don't worry about this. Like this is basically, I just call this K here. And this K here should be, yeah, yeah. I don't worry about that basically at this stage. Um, and B here, okay, this one again, like the for what is, maybe I erase this here now again, not to confuse you guys. So for this one, let's expand again. So this one is like given the class PB here and PLSY given B here over, just call it K here, just over K here. That would be the probability, right? And then like now using the conditional independence assumption, I have PL given B, PS given B, PY given B. So let's make some questions here. So, oh, wait, where's that? Yeah. So what is PB? Can you find PB out of this table here? Let me pull this table like, no, you're good. Yeah. So, oh, based on this data, actually, based on this data, you should imagine like this. Like, okay, of course, when I in general, like ask like what was the probability of getting a banana out of a forest, like it would be different from what we get from here, right? So what we make the assumption here is like we yeah, okay, but anyway, I see like, oh, you guys, I got it. So yeah, so we are assuming like, oh, this is a, we have, this is the training data here, and that this test data should have the same distribution as the training data. Otherwise, it doesn't make sense. This is one very important rule for like machine learning. it's like your training data distribution should be the same as the test data distribution. If they are not the same, then there's no point of using that training data. So therefore, like I can also assume like in the test data it's have the same distribution. So therefore, like yeah, the probability of banana is just like 500 over like 1,000. So therefore, it's 0.5 here. So how about what's P suite, like let's say P S given B here? What's this one based on this table here? Yes, sweet given banana. So everyone is good with that. So let's see. Sweet given banana. So we can use base rule here, or actually you can read it directly like uh PS and banana, both sweet and banana will be like this one, right? 350. Or like I should say this is like 350 will be like equal to sweet and banana will be like 350 over like 1,000, right? Out of like 1,000, I have 500, 350 of them are both sweet and banana, and P banana is like basically 500, right? Over 1,000, so it's like 0.5. So therefore, this over this one, so it's like 0.7. Yeah. So I guess that you can try to. Okay, this is let's see. This maybe take a longer time to compare. I don't know. Like maybe I ask one more, a couple more. Let's see. Uh, so so of course, as I mentioned, the entire probability should be equal to this one with a normalization factor, right? So this I don't care for the moment, or like this is equal to PLSY here. Uh, and let's just like what's the numerator here? Just like the entire numerator. Can you guys like compute this one? Yeah, cool. Yeah. Uh, yeah, probably you need a calculator. Yeah, I think that too. Yeah. Um, let me try to calculate octave or something like that. Let's see. Yeah, I think you guys are right. So yeah, so basically I have this one. This is zero point 0.5, right? We compared earlier, and this is 0.7. And switch given. Oh no, actually this is 0.7 that we compared earlier. This is 0.7. This is zero point 0.8, right? So out of the banana, like 400 of them are actually long. So 455 over 500 will be zero point 0.8 here. And then for this one, like out of like 500 there, like 450 are yellow. So that therefore this is zero point 0.9 here. So if you multiply them together, should give you a number like 0.252 here. So good. So of course, like this is not exactly the probability because we still have this normalization factor here. Okay, this will be a longer question now, so I don't know, but hopefully, uh, so what's this value then? You should not be more difficult, but it's just a bit more computation now. Then what is this one now? Oh yeah, sorry. Yeah, of course. Yeah. Let me move this thing like down here, or let's just copy another one here. Yeah. Yeah, probably. Let's see. Yeah, it should be larger like this. Yeah. So but you guys are computing, like doing the calculation. Do you have do you go stuck, or like do you have any question? Like, yeah. So know that, like maybe I know that this one, like, okay, we compute the numerator is this one, but uh this guy should be equal to this PB PL given um L given B. Let me erase this number here. PS given B, Py given B over this denominator, this K here is actually PB PL given B, PS given B, Py given B plus P, what's that? Orange, PL given O, PS given O, Py given O, plus others, Px, P given X, PS given X, Py given X. Yeah. So actually for the orange, you see that like PL given O is just equal to 0, right? Because for out of all the orange, right, there no orange is long. So actually this one is gone. Like you can forget about this one. So you should compute this guy and then like, yeah. So any okay. Anyone has any question if like here? Like, is that reasonable? So because we have this, I remember why we have this again. Is we have this one is equal to this guy is equal to this numerator over some constant independent of b, and then I have like PC as well. Oh, sorry, PC. I don't have PC. PO given L S Y will be essentially very similar. PO, PL given O, PS given O, PY given O over another same constant K here, and so forth. And and because I have this conditional probability, if I sum over like B taking value B, taking value O, and taking value X should add up to 1. So I have K is essentially just equal to this. Right? Yeah, I want to make sure this add up to 1, right? So I will force my normalization factor will be like this one. Just yeah. Um you guys agree with that? So maybe so I want to make sure like I didn't write here that like I lost anyone like jumping from this one here to this one here. So what I'm using is basically saying that like I have P. Let me just say write a variable f here like as float. Float given this features here. Uh, or maybe I just write LSY here anyway. SY here. Um, PB given is equal to P. This okay. Okay. Let me just write like this. Yeah. equal to 1, right? So therefore, like I know this thing here is equal to this long list PB whatever over K, and this here is a PO something something over K plus P uh, X over K is equal to 1. Then I just pull K to the other side, right? So therefore I got this constant K. The denominator, the normalization factor is just equal to this if you add together. Right? So therefore I have this as a K now. Yeah. So okay, nothing really mysterious. Um 969. It seems right. I forgot. Let's see. Uh yeah, I don't know. I didn't get the same value, but maybe you guys compute correctly. Let me try to do it again. So I think this PO thing is equal to 0, right? So PO thing is 0. Oh, okay, if all you get the same value, most likely I made mistake. So let's say this one here, PX is equal to others, I say zero point 0.2, right? So PX is 0.2, PL given X is 0.5. Let me know if I made a mistake here. So um, PS given X will be, oh yeah, I made a mistake here. I think this is 0.75, right? Yeah. Oh, no, this is 0.75, right? For the others, I switch like, yeah, 0.75. PY given X is a 0.25, right? Yeah, it's 0.25. So therefore, like I have this one is equal to, is that right? Is that I'm doing correctly? So this one I should 0.2 times 0.2, 0.2 times 0.5, times 0.5 times 0.75 times 0.25 is equal to 0.01875. And then, so therefore, like this probability should be equal to 0.252 over 0.252 plus 0.01875. Right? Is that? Huh. Yeah, but somehow I got this value is 0.93075. I don't know why. I see. Hmm. I can show you my number. Maybe you can, let's see. I have 0.2 times 0.5 times 0.75 times 0.25 0.0. Oh yeah. But that's okay. Like you're good. Like you think using just a yeah, and then like okay, it's like 0.252 0.01875. Yeah, I think like this would be so anyway. So you see that, right? So if a nice thing about life base is like you can get the exact probability here. Like you get like not just like whether the best class it is, like you get some kind of probability, at least some belief, right? So it may not be completely accurate, but know that the only assumption it made is like the conditional independence. So each feature is a conditionally independence given the class. So therefore, like the tendency is like if the class is more descriptive, then as I mentioned earlier, for example, if I made the example that if my cat species say is more have finer granularity, so maybe I go down to short hair cat, like short hair is a short hair or like long hair, that kind. Then or yeah, I'm not very good with like uh, different species, but if you go down to all this detail, then knowing the particular species, then like you can know precisely like what's the um, shape of the ear is like without knowing what's the shape of the nose, let's say, of the same object, same subject. So therefore, like in that case, the features will be independent, conditionally independent given the class. Um, so, but if your class is rather broad stroke, like this case, I only banana, orange, other, then most likely this assumption probably is not very good. Like yeah, but that will be a trade-off if you have like final classes here, as you can see here. Like I will need to compute more values to compute this conditional probability, right? Because I need to compute like this term for every classes to get the normalization factor here. So, but anyway, like that's life based. So very simple. So I hope that like you get now, like if you don't know life based before, I hope you understand everything about life based now. And also, actually, sometimes people also introduce something known as the Laplace coercion. Is that like they don't want to have um the value to be too extreme. So in the sense, for example, for this one, like it's kind of exclude all the say like all the orange cannot be long. So orange has to be long. But it of course it may be a fact, but it may be some kind of error as well. So sometimes I if this is an error, this is will just like make this probability one of the feature. If I have something like this, then okay. Yeah, if one of the probabilities have something like this, for one condition, sorry, for one feature, if it has a probability like this, conditional probability like this, then no matter what the other features, I say like it's actually orange, let's say the other feature all saying like this is an orange, and so on, right? But it can never like change this, overrule these features because like, it's so confident that it's not an orange. So therefore, like doing a Laplace coercion will be like maybe instead of like saying like very kind of confidently like there's no orange to be long, we just say that okay, this can be like one orange to be long, something like that. So have a small adjustment to just like make it possible if like all the other features saying that like no, you are not white, then there's a chance that they can overrule that. Yeah. So this is like known as Laplace coercion. So okay, basically this is the everything I like to talk about for uh, naive based algorithm. So if if you have any question about that, like I can answer that now. So if not, then I guess this is more or less I I the entire review I want to do like for probability. So to end it, like I guess I will give a kind of like talk about very interesting problem that huh, you probably like some of you like heard of that before, but maybe some of you don't. Uh, so maybe it's good to talk about to think about that. So just another probability puzzle here. So this is like long at like I maybe I shouldn't give them. Oh yeah, it's okay. I put the name there like in my kind of like calendar anyway. It's known as the Monte Hall problem. So it's a kind of like a problem based on a puzzle based on a game show. So it's like not kind of a real game show, but it's like kind of like something I don't know. Like I didn't watch this on TV before, but anyway, so maybe you saw this before. Um, basically like there's three door here, and then like there's a prize behind one door, and then like you have the host and a guest here. So basically, what the guest is going to do is like um the guest is going to pick a door, like any one door. Let's say I have three doors here, A called A, B, and C. So the guest will pick one of the door and try to guess which door have the door price. And if he pick it correctly, then of course he get the prize, something like that. So now what he do is like okay, pick the door, but the game doesn't end here. Then what the host is going to do is going to open one of the another two door that doesn't have the price. And then of course I open the door that doesn't have the price. And then like afterward, I will ask the guest whether he want to switch his decision. So let me just like give one example here. Let's say I have guest here, pick this door here, like he first pick. Guest pick this one. Now the host will then open one door, like maybe let's say that the of course it will open only the other two doors, uh, kind of like except the one he picked that doesn't have a price. In this case, would be this door, right? He opened this door here, host open this one. Now then the guest only see this one and okay. Then of course then okay this got open here now, and then voila, there's no price here. The guest see that, oh, no price here. Now the host will ask the guest whether he want to change his choice, whether he want to still stick with the original choice, original pick, or want to pick the other door. So then the puzzle like is like, okay, what is the best strategy for the guest? Like, should he switch the door or shouldn't he switch the door? Maybe just like a in kind of like just okay, yeah, I mean, yeah, that's good. Okay, this is like just one for one. Okay, this is one realization, right? Okay, for of course in this case, like he should switch the door, but I mean in general, like should he in general should he switch? Should the guest pick the other door? Okay, yeah. So okay, I guess many. That's good. I guess after two almost two classes for probability review, I mean like you're better than many people. Like actually, this is actually very. If you look at the, I mean, search the history, like you go to Wikipedia, search this this problem. This is very interesting because um you have like PhD or like statistician talking about this problem, and then kind of like gave the wrong answer, and that's involved like people like I said like extremely high IQ. I forgot like who a lady have like very high IQ, but he's like not a mathematician or whatever, but she argued correctly like I mean get the correct solution. Like even like some PhD made mistakes like for this one. Um, okay, but anyway, I guess I all of you agree that like if he doesn't switch the door, the chance of like getting the price is one third, right? If not switch, probability price is equal to one third. So I think you all of you agree with that, right? So it seems very reasonable, right? He start from the big. Okay. If he doesn't switch, if he doesn't switch, okay, maybe okay. Maybe then I should ask this question. Then I just assume I didn't say that. So what wait, yeah, that's the thing. If he stick with the original decision, whether someone open the door shouldn't change the probability, right? Because like the decision is made before like he opened the door. Like you cannot like have the host like open the door, then suddenly change the probability, right? Because like does it kind of make sense? Like so think of like now if you think of like the host is not doing anything, let's say he has a price here, the guest randomly pick one door, then the chance of getting the price is one third, right? So now the host open a door that doesn't have a price. Now, if he stick with the original decision, then it shouldn't change the probability, right? Because nothing really changed. Essentially, it has this information given by the host, but it shouldn't change the probability, right? Because the host is not going to back to the stage and suddenly swap the door, swap the price, right? The location of the price, right? It just it reveals some information, but because you're not using that information, like it doesn't change the probability. And it will change the probability if like the holes actually go under, like, and then like move this kind of like price like from one door to another door, then we change the probability, right? But he didn't do that. He just opened the door. If we stick with the decision, then the probability should stick to the same. So therefore, still one third. Uh, hopefully, Richard, do you agree with that? Like still, or I mean, or do you still think that like it may change the probability? Okay, yeah. So, but you agree with that, right? So, I mean, like, if we stick with that, like, it shouldn't change, right? It shouldn't change the probability. Like, so therefore, like, if we stick with that, the probability is one third. So that's the thing. So now the question is harder and more interesting. So if he switch, what's the probability of price? Yeah, which I thought like that, like also like when I first I think of this problem, yeah. Uh, I think like it's a yeah. I guess I okay yeah. Um, this is interesting, yeah, right? So I mean, yeah, this is not obvious. Like, we should go to the first principle, like engineering way, and see if we can like just think of that like step by step. So let's think like we have like several yeah, he only between two doors. I know that there's only three doors. The host open one door, then there's only another door. Like he can stay with his decision, or like he can switch. Now, yeah, if you stay, then it's just like nothing happened, right? So the probability should be still one third. But if we switch, yeah, that's the thing like get everyone, many people confused like what the probability will change. And so let's see like why. So I guess I remember like last time, like last class, we say like probability is like oftentimes ended up into some like combinatorial problem. You're just counting different cases essentially. Like you just list all cases and you will see the answer. So I will just like without loss of generality, I will assume that like the guest pick this one. Let's say the guest pick this one, right? So and then like there's several different cases. So I can have like the price. Let's say I have three different cases here, right? I have three different cases here. So I assume like all of them, like the gas, I pick this one. This is the gas pick this one. And then I have the first case, the price is right here, right? And second case, I have price right here. Third case of price is right here. Let's say. Now let's consider the first case here. The first case, the gas like pick this door, then the host open one of the door, right? Then let's say like the door open this one. Now if we switch the probability of like getting the price, so maybe this is like I call it like probability like switch. Okay, maybe I just write probability of like price given switch. Or maybe I just or make the switch. I understood that like for all of these cases I'm going to switch. price given that like um pi door one, maybe I just like win here, maybe equal to zero, right? So if we switch, like in this case, if we switch, let's say price is like in the one here, then it will basically say zero, right? Okay, you guys see it already now. So, and then for this one, like what? So of course, like, the host can open the other door, but it's still the same, right? The probability is still zero. Like in that case, like no matter what, I mean, which door the host open, like still like I will get basically like the guest will lose if he switch. Now for this one, like if the price is here, the host can only open this door, right? So if he switch, he win, right? So therefore, like probability win given price in two is actually equal to one, right? I'm actually the same in this case as well, right? If here, then the host can only open door here. Then if we switch, then again, like he will win. So probability win given price equal to three is equal to one. So because we assume that like the price is randomly placed like uniformly like for all three cases, so each of the case have like same probability. So therefore, like the probability of winning is like just two-thirds. Yeah. So therefore, like he should definitely switch. That's the conclusion basically. So this is the uh, Monte Hall problem. Hopefully you guys enjoy it. So this kind of conclude the review on probability. And at this stage, I think you're better than many PhDs like, on this mathematics or statistics or whatever. At least like for this problem, like many people got stuck. I got stuck when I first heard of this story. Like I when actually I hate this. I was in a kind of like I was in a trip and I don't know like I'm very bad with car. Like I got kind of like car sick or seasick. Like it's a kind of like this tour bus, and then like my friend is like asking me this kind of question, and I have headache, and then I mean just say, yeah, you're wrong. Yeah, I know I'm wrong, but I it's not the time I can think. Like anyway, so but yeah, so but anyway, this is actually in fun puzzle. So I guess for the rest of the time, I want to give a very brief introduction of Monte Carlo. So this lead to kind of like something like in the title of the course is probabilistic programming, because I of course you can see that like many of these probability problems like we can do some kind of analysis and uh trying to like figure out this like analytically like write down the exact precise solution. But this is usually not the way that is able to solve like most of the problem. For most of the problem, like it's solved by using simulation. So that's where Monte Carlo, the name like kind of like reason have this Monte Carlo here. It's like we do this like by just simulating the thing. So for example, like if we go back to the example we have like at the beginning, we have this whatever W like flip have a coin like start with a head, and then like we have X is like folding a dice here, and then like you depend on the dice of the value of the dice, are going to flip the coin or not. Then maybe I got a tail, and then like Y and Z and so on. So I can ask like lots of questions. Like for example, like what's the probability Y is a tail and probability of Y as a tail given W is a or W maybe it's already had like or like maybe C is equal to tail or something like that. Uh of course you can compute that numerically, right? That's definitely you can do that. But another way to do that is just by simulation. So you can do experiment essentially like just assuming you're going to repeating do this experiment many times. Let's say if I want to find the what's the probability of Y equal to tail, so what I can do is like let's say I would do this experiment like 1,000 times, and then maybe like out of this 1,000 times, I have like Y is equal to tail with like 512 like so many of times. then I can assume like this will be approximately the probability of that y is equal to tail will be like 512 over 100, 1,000, then it will be like 0.5112, something like that, right? Let's say. And we can ask a more complicated question, like also using simulation. So let's say I want to ask like, what's the probability of like y equal to tail, uh, y is tail given z is tail, let's say. So again, I can do experiment. Let's say I do it like again like 1,000 times, and then like now here um I cannot directly get the outcome, right? But like a simple outcome like this, I just looking at like how many tail I got like from y. But I can use space rule, right? Here like I can use space rule. This is like equal to probability y equal to tail, c equal to tail over probability c equal to tail. Now this one, of course, I can use base rule again. No, not base rule. I'm sorry. I use like simple counting again. So let's say like in the experiment, I have like 300 of them is a is tail. So therefore, I can approximate this as a uh, .3, something like that, right? And for this one, maybe like have like 180 of them are both like Z's tail and Y's tail. So therefore, I can approximate this as like 0.18, something like that, right? So therefore, like using this, I can approximate this conditional probability as well. So so you see that just simply doing actual simulation, you can approximate any probability. But then of course, like the problem is like, how do you do the simulation? For a problem like this, it's quite simple. Because for example, like I can do experiment by just following like precisely in computer. I I would just try to simulate. Let's say if I have this start with a hat here, I can simulate like whether I got a head or tail here. By the way, how do I simulate that? Like I need to simulate following a dice, right? So that would be like trying to so if I try to okay here, I will basically just really try to follow a dice, right? So of course, if you know some of these function, like maybe Python or MATLAB or whatever, I need to probably take it up. But there's always some random number or like random int or like something like that, right? Let's see. Let me check. Like for example, like MATLAB, what kind of like uh uh what's the maybe I use NumPy. Oh yeah, NumPy has a rand in, but like MATLAB doesn't have a rand in here. For example, like I can oh I try to pull this one. I so difficult to pull this out. Come on. Oh yeah, it's okay. Yeah, let me just copy that. So if you are NumPy, you can stay NumPy random. There's a rand integer here. So maybe rand in 6, that will give me a integer, a kind of like random integer from 0, 0, 1, 2, 5, three, four, five, right? Six number, something like that. So you can add one to get like 1 to 6 if you want. So then uh, I can, this is like basically a uniform distribution. So whenever I get a five, in this case, I will assume that I got a six there. So therefore I will flip the dice, right? So I can basically use that to do the actual simulation, right? So I can um, basically see, like, let's say I call this value V here. And if V is uh, equal to 5, then I'm going to flip the value. So basically I have W of X is equal to uh, not X. Oh, I don't know. Like maybe, okay, this is a pseudocode here. X is equal to log W, something like that. Otherwise, else X is equal to W, something like this. So so this is like if you have like kind of like what I mean is like if you have like discrete random variable here, you can simulate this way. If you have uniform, like um, for example, like if I want to kind of simulate whether is uh, probability x is larger, let's write like this. Let's okay. Let's make a new variable here. U here. U is like just 1 or 0, and U is 1 with probability U is 1 is equal to point some arbitrary number. Let's say it's equal to pi over 10. Let's say. So in this case, I you and let's say like otherwise it would be equal to 0, right? In the sense like probability U equal to 0, or like 0.314116, something like that. So this is a 0.6. I don't know, a 584, let's say, right? Something like that. Now, how do we simulate that? In this case, it's not an integer, right? So in this case, we may simulate this using a uniform random number. Say, let me find the what's it? Um, yeah, okay. If I'm using NumPy, I can also like oh, by the way, like I'm using NumPy, then I should be have something like import NumPy as py, something like that. Oh, sorry, as mp here. So of course, I'm mentioning this because I'm thinking like I will have a tough question uh, like this for your first homework. So therefore, I want to kind of like briefly describe like if I know like many of you should know this already, like how to simulate a do Monte Carlo simulation. But just in case if you don't know, let's say if I try to create a random variable, let's say like to be one with some probability, like this is a rather arbitrary, it's not something integer, it's not exactly equal to 1/6 or whatever. um then you can just say create another variable. So just something like again call this um maybe a here is like numpy random uniform. So for example, I can do something like that. So I'm just doing this in the sense like because I know how to do it. Like it's probably not the best way to do it. Like that's probably you can find like other function to do it. But so so this will create a random number. Is from 0 to 1. It's a continuous number, continuous random variables here a. So I can say like in this sense, then I would say u is equal to um, 1 if a is less than 0.31415, right? Else 0, something like that. Then it will work. Um, so uh, oh wait a sec. Like yeah, I guess okay. This is basically like if you guys have no problem with here, like I'll just stop this part. Like maybe just go back like uh Richard has like some comment with the Monte Hall again. So he said like 2/3 is wrong because if guess pick correct door first. Okay. Then there's two simultaneous switch door which will cause them to lose. Yeah, but this also like have yeah, it's okay. Like we are kind of done here. So but I guess I um uh we can continue this discussion. Anyone like if you want to stay like for this discussion, like you can stay. Otherwise, this is basically all I like to talk about today. And then probably I will post a first homework like today or tomorrow. It will be due in 2 weeks. That will be like just also like have some review for probability and also like doing some simulation as I mentioned here, like trying to kind of like estimate some probability using simulation rather than like trying to kind of compute it like analytically. So okay, like yeah, sure, like we can talk about that like in next class. Yeah. So okay, I'll yeah I can repeat a little bit like next time. Yeah, maybe give an example also. So I'll see you guys next week then. Yeah. Okay. Bye now. Yeah, sure. I talk to you guys then. Oh yeah, and by the way, like again, like if you have other questions, like uh, just send me to Discord. Like I will respond like as soon as possible. Yeah. So okay, I will stop the kind of like hearing no other kind of I will stop now.